In this video, we're going to introduce the concept of the mole fraction. In the previous video, we talked about Dalton's law of partial pressures and how it defines the pressure exerted by each component of the gas in a gas mixture. Well, the mole fraction is a way to quantify the amount that a particular component is contributing to the gas mixture. It's literally the ratio of the number of moles of one component. So let's say we have one component one, it'll have a number of moles in one. It's just going to be that number of moles over the total number of moles of your mixture, right? So in one over in total would give you the mole fraction for component one. And the symbol that we use for the mole fraction is the Greek letter chi. And so I'd usually write chi as like a curly X here, right? So chi 1, right? The mole fraction for component one would just be the number of moles of that component over the total number of moles in the mixture. Now, the really amazing thing here is that because of Dalton's law, we can relate this directly to the partial pressure of each individual gas, right? So think about the ideal gas law, right? If we think to the ideal gas law, we can isolate the number of moles, right? We start with PV is equal to nRT. Doing some simple algebra, we know that N is going to be equal to PV over RT. So what that means is that if we wanted to re-express both of these number of moles, right, in terms of the pressure, volume, gas constant, and temperature, right, we can do that. So we can have N1 would just be equal to the partial pressure of that first component times V over RT, and in total would just be the total pressure times volume over R times T, right? So this will be N1, this will be in total. We can actually plug those into our expression for the mole fraction, right? So we have chi 1 would be equal to P1 V over RT over P total times V over RT. So algebraically, right, these V over RT terms cancel out, right? So this guy cancels with this guy, right? So then we just end up with the following, where we have chi 1 is just going to be equal to the partial pressure of that first component over P total, right? So this is the definition of the mole fraction, right? But you can also relate the mole fraction to the partial pressure of that component, right? It's going to be partial pressure over the total pressure will give you the mole fraction of that component in the mixture, right? Giving you the ratio of how much that component is contributing to the overall composition of the mixture just from knowing the pressures. So let's look at an example of this. All right, so this problem says a mixture of cyclopropane and oxygen gases is sometimes used as a general anesthetic. Consider a balloon with an anesthetic mixture of cyclopropane and oxygen at 170 torr and 570 torr respectively. Calculate the mole fraction of cyclopropane in the mixture, right? So let's map out what we've been given. Each of these pressures, right? So they're giving us the partial pressure for each of these components of this anesthetic mixture, right? Cyclopropane is at 170 torr, and the oxygen is at 570 torr. So each of those will be a partial pressure. So I'll have Cp for cyclopropane. So the partial pressure of Cp will be 170 torr. And then the partial pressure for oxygen, O2, is going to be 570 torr. Right? Okay, so we've got the partial pressure for each one of these. They want us to calculate the mole fraction of cyclopropane in the mixture. Well, based on that definition that we saw in the previous slide, right, we know that the mole fraction for cyclopropane will be equal to the partial pressure of cyclopropane over the total pressure of the mixture, right? We already have the partial pressure. All we have to do is calculate the total pressure in order to get the mole fraction of cyclopropane in this mixture. So let's do that. So the partial pressure, the total pressure should just be equal to the partial pressure of cyclopropane plus the partial pressure of O2. So if we sum both of these guys up, we got 170 torr plus 570 torr. And so that's going to give you 740 torr. So our total pressure is 740 torr. So to calculate the mole fraction for CP, right? We have the mole fraction for CP is just going to be the partial pressure for cyclopropane, which is that 170 torr, over the total pressure of the mixture. So that's the 740 torr. Right? So when you do the math there, right, your units cancel out. So you end up with a unitless ratio, which is exactly what we want here. It is just like a ratio or percentage. So we get 0.23 as the mole fraction of cyclopropane in this mixture. And you can think about this in the way you would think of a percentage as well. This mixture is going to be 23% cyclopropane, which obviously means that the other 77% will be composed of oxygen, right? So basically this type of calculation is made possible by Dalton's law. By Dalton's law of partial pressures, we're able to gain insight into the composition of a gas mixture just based on the pressures that these gases exert in a container in a mixture.